Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Well, up until this point, we've been doing a lot of historical aspects and discussing how things arose out of the miasma of early pre-science. And we got through Kepler's struggles with Tycho Brahe, and we got through Galileo's trial and all of his difficulties and his findings. And yet we were left with something very, very, very important. What we're left with is that it's an unfinished business, because even at the end of Galileo's life, when he wrote about the motions and how things move, it still was not understood exactly how the cosmos worked above. So here's the thing that starts to happen. Everybody's talking about it all over Europe in the 1660s, assuming Kepler's laws are true, or at least work extremely well. And brilliant minds all across Europe are working feverishly to try to understand it. So it comes along in 1684 that Edmond Halley in London, Edmond Halley, Christopher Wren, and Robert Hooke are all sitting around talking, and they're in a conversation. And Hooke claims that he has derived an inverse square law that shows how the planets move, and actually shows how the planets move around the stars and derive the orbits of the planets. However, Halley presses him on it, and Hooke never actually reveals where he actually does it, or even reveals his writings. He just says, I've done it, but he never actually shows any of publication. Anyway, so because this is so pressing, and Hooke is just kind of this really strange fellow. Oh, by the way, a really good story for where you can see this in a nice dramatic format is, I'm just going to cut away here for a second. Go see Neil deGrasse Tyson's Cosmos series that describes this particular effort. And it's a wonderful dramatization. So I'm going to kind of summarize pieces of it here. But basically, it's a pretty well-known topic. But let's continue on in 2-minute format as opposed to half-hour, 45-minute format. In any event, so Robert Hooke is basically a fellow that basically is domineering. He's just kind of a grumpy sort of little guy. And then there's this young man, Sir Isaac Newton, who is also over at Cambridge. And Halley goes and visits Newton over in 1684, knowing he's, after this conversation, probably around August or so, visits Newton and tells him about what Hooke told him. And Newton says, oh, I've already done it too, and I have it written down somewhere around here. I'm not sure where it is, and his papers are stacked. He's like a hoarder or an OCD kind of guy. He's also a mystic, and he's a very quiet fellow, so he doesn't feel like causing any controversy, because if Hooke says this thing, he doesn't want to get into a tussle with Hooke in any event. So Newton said he's already got it, he already finished it a long time ago. Halley's stunned. These two people have finished this thing, and neither one of them wants to talk about it. So it gets kind of crazy. But Halley persists and says, you really should do this. And Newton says, well, if Hooke hasn't done it, I guess I could do it, or maybe I'll show Hooke, or something like that. There was some deep competition between Newton and Hooke. And between about May of 1684 and the summer of 1686, Newton actually worked almost primarily on the Principia, which is his masterwork describing the motions of the planets and the work of gravitation. He invented the calculus in order to do it. Newton's secretary says basically there were no notes on anything that Newton would talk about on any other subject of this during that time period. Newton was also known to be extremely eccentric in a lot of ways, and he would just go out on long walks, and he'd forget to eat, he'd forget to bathe, forget to change his clothes. Sometimes he would go out walking, get a new idea, and run back in. Fairly standard obsessive. But Newton was a brilliant mind. And by 1686, the summer of 1686, Newton had written his books. And Halley then presented it to the Royal Society, and said, we need to actually publish this. And they'd already published, they'd used up all their money for publications on a publication about fish, diagrams, illustrations of fishes. So they didn't have any money to publish this. But Halley thought it was so important that what he chose to do is he chose to use his own personal money to publish solo Newton's work. So the Royal Society gave him the go-ahead, and it was published in 1687, his Principia, Newton's Principia. And the Principia is considered to be one of the greatest masterworks of all of science. And in it, he describes his laws of motion and his law of gravitation. So what are Newton's laws that can be summarized out of the Principia? Well, they're the classics. The first law of motion says that any object that is at rest will stay at rest, or any object in uniform linear motion will stay in motion unless it is acted upon by a force. So it'll either keep going straight or stay at rest until it's acted upon by a force. Now notice this actually kind of holds with Galileo's idea of the things inside a boat. So basically the rock inside, or a ball inside the hold of a ship as a ship is going steady, is actually, there's no net force being applied to the ball inside it as it's dropped. So it keeps its motion, because it doesn't matter, according to Newton, whether the ball is dropping or being held by a person. It has a speed. The ball itself has a speed going this direction. When you release it, it then falls under the course of gravity, but it still retains that speed due to Newton's first law. So there's no new force acting upon it except for the downward force, which is gravity. So since there's no new force, it makes total sense why the ball falls straight inside of a held ship. And also it makes sense why if you set something on a table, it doesn't move because there's no forces acting upon it. And something rolls straight across a table. If there's no additional forces, it keeps going straight. If it starts to turn, then maybe there's like a curvature, or maybe there's somebody attached like a string to it or something. But if there's no force to it, it'll keep going straight, or it'll stay at rest. In any of the next thing is like, well, then what's a force? A force is defined by Newton as being a thing, any action, some action that accelerates a mass. So if you have a mass, something that has mass, and it is accelerated, then a force must be applied to it. So if you start from speed 0 and you end at speed 60, you must accelerate from 0 to 60 miles per hour, kilometers per hour, miles per second, what have you. But it would be accelerated. So in order to go from 0 to 60 miles per hour, you need to accelerate it using a force. And if you wish to decelerate something, or negative acceleration, then you would also apply a force, which might be brakes or something like that, or a rocket engine going against the direction you're going, or a hand stopping something. So forces cause masses to accelerate or decelerate. And that is a property of this thing called mass. So if a mass is accelerating, then a force must be being applied. Now, acceleration is a strange thing, because we tend to think of it in terms of speeds, right? But what now Newton then added the idea that it's not just speed, it's also direction. So an acceleration is in a given direction in addition to at a given speed. So speed is just how many meters per second is it changing every second. Like if you're accelerating from 0 to 60, maybe you do that over the course of 6 seconds. So it's 10 meters per second per second. That would be your acceleration. So that would get you up to 60 meters per second in 6 seconds, 10 meters per second per second. So, but let's say now you are keeping the same speed and you're starting at 60 meters per second and you start turning to the right. Now you're not going in a straight line anymore. So therefore you must be accelerating. And so the acceleration is also a change in direction at the same speed. So which you can use that as an idea to derive planetary motion, because planets go in ellipses around. So they're changing their direction. Kepler said they also change speed, but let's for a second assume a perfect circle orbit, which we know from history doesn't really exist, but that's not the point. The point is, if you had a perfect circle and it's orbiting in going around in that perfect circle, the speed would never change, but the direction would. So therefore, a force is operating on it. If there's a force operating on it, what's the force? All right. So in addition to forces operating on things, you can't just have a force that doesn't push back. So Newton's third law of motion is equal and opposites. For every action, there is an equal and opposite reaction. For every force that is operated upon, there is an equal and opposite force the other direction. So when we think, wait a second, we set something on a table, the force due to gravity means if we pull the table up from under, the thing would drop, right? So what is actually acting against the force of gravity? The thing that's acting against the force of gravity is the push by the table up. So you set something on a table. You stand on a balcony or something. The balcony pushes up against you, against your being pushed down by the force of gravity. So there's an equal and opposite reaction for everything. If you wish to accelerate a car to 60 miles an hour from 0, what are you forcing against? Well, you're forcing against the ground. The car is pushing against the ground. So what's the ground doing? The ground has to push against the car with the same force that the car pushes against the ground. So everything's opposite and reactive. And another way of looking at it, a classic problem you'll find in a college physics course is imagine that you're on a flat lake of ice. And I grew up in Minnesota, so everybody always talks about going out in the ice in January. And so you go out in the ice in January, and what do you want to do? You get stuck. Maybe your car runs out of gas. You have people drive cars out onto the ice. So your car runs out of gas. So can you push your car off the ice? Now, this is a good question. Now, if you're wearing crampons, meaning like spikes on your shoes, then in theory you could, because if the rubber slides on the ice better than the crampons do, then all you have to do is overcome the friction across the ice. Now there's a lot of friction. Friction depends on the mass and the pull, so the car might be sinking into the ice harder than you can push against it. So, but in theory, you can push things around if the balance, if there's a balance, if there's an upward and downward balance against it so that there's no friction. So that's why we can think, oh, if you put on ice packs, how much friction does it take? How much push does it take to push across an ice field? But let's say there's no friction at all, and you just go up to the car, and you're both on ice, your tires are slippery and your shoes are slippery, and you push. Does the car move? And the answer is yes. You force on the car, and the car forces on you. But remember, the forces are equal and opposite, and the acceleration is dependent on the mass. So the lower mass thing, meaning you pushing against the car, gets accelerated more. The higher mass thing, the car on the ice, gets accelerated less. But they're equal and opposite. So the product of the mass times the acceleration for you is equal to the product of the mass times the acceleration for the car on the ice. The car is more massive, so it accelerates less, which is really interesting. So basically, yeah, you can, but it's going to go, you're going to have to push a lot, and you're going to be pushed away from the car far more than you will push on the car. So it's not practical to try to push your car off the ice if you're stuck out there after going ice fishing, and then you find yourself your ice shack. You need to go off and get some supplies at the corner store in order to make it through yet another cold Minnesota winter. So basically, Newton's 3 laws help summarize and understand how everything moves in the cosmos. Meaning, if there's a force acting on something, then it changes speed, it changes direction. Or let's say you drop something. Let's say as you're moving and you're going at 60 miles an hour, and all of a sudden a big chunk of something falls off the car. Could that actually work? Maybe it's an acceleration. Maybe you have a rocket engine and that has mass to it. And as you expel the mass, you actually go faster. So if you drop the mass, you can actually accelerate faster too. Anyway, there's a lot of ways to do things like this. So those 3 laws encapsulate equal and opposites, F equals ma, and the rest and at rest of the definition of momentum. Basically, the first law is called a definition of momentum. And if a thing that has 0 momentum, the product of its mass times its speed is 0. And if you're going to change momentum, it always has it's a conservation of momentum. That's what the number 1 law really talks about. In any event, so the last one that he talked about is he said, all right, now, the planets. How do the planets go? The planets operate under a force that he called gravity. And gravity is a special kind of force. Now, how is it defined? He defined it as a fundamental thing. The force due to gravity is proportional to the two masses that are gravitating against each other, the product of their two masses, divided by the distance between their centers, squared. So the product of the two masses divided by the square of the distance between them is proportional to the force that they have to each other. So in order to actually know what that force is, you have to measure that proportionality constant. So frequently you'll see F sub g, or a force due to gravity, is equal to some constant, big G, which is Newton's gravitational constant, times one mass times another mass divided by the distance between them squared. So it is now this constant of proportionality, big G, not little g. Little g is the acceleration due to gravity at the Earth's surface, but big G is the measure of how strong the acceleration due to gravity is on a given mass. So let's say you have all these things, and that's Newton's positing that exists. He posits the force, the inverse square law of the distance. He posits that the force is due to the masses and only their masses. So gravity operates over a distance. It operates only between masses. And that's really something very interesting. So when this happens then, remember we said that a force exercises on something if it changes direction. So now let's pretend we have a circular orbit. And Earth's orbit is almost perfectly circular around the sun, almost. So it's a good example. So as the Earth goes around the sun in its almost circular orbit, as it goes around, we can actually say, well, what's the force that's causing it to go in that direction? So F equals ma is equal to the gravitational force, gmm over r squared. What are the masses? Wait a second. The mass of the Earth is in there, and the mass of the sun is in there. So there's an acceleration. How fast is the Earth accelerating? What is the change in the speed? Meaning the change in the speed as it goes around the sun. Well, its linear speed around the circle doesn't change too much, but its directional speed does. Meaning it goes in this direction, then 4 months later it's going in this direction, then 3 months later it's going in this direction, and 3 months later it's going in this direction. So the direction of the speed is always changing. And so therefore a force must be acting upon it. All right, so we then equate these two, take into account their directions, and play a whole bunch of algebra and math, and we find that this can actually help us get to the laws of orbital motion. Now, notice I said that the changes in speed, change in anything through time, is the basis of the calculus. And calculus is one of the branches of mathematics that everybody in college learns when they take physics classes, or it's one of the first things they take in the math major and so forth. Almost everybody in college who has to take a math class has to take a calculus course. So calculus is simply the way that we derive and measure changes of things with respect to another thing. So what are we changing in accelerations? We're seeing how speed changes with time. And speeds themselves could be looked at as how do we change distance with time? All right. Forces show how the acceleration, or forces dictate an acceleration. If the acceleration is constant, then the constant change of speed with time. So that also makes directions as well. So the calculus was a way of saying, how can we do these tiny changes in speed over time in order to show orbital motion? What's funny is that the concept of orbital motion and speed and changes was actually kind of thought out in very rough format by Galileo in his dialogue concerning two world orders, as well as by Kepler and many of his contemporaries. They all thought about this change in direction and change in speed as things go around. But they had a really difficult time formulating mathematically. Kepler's mathematical formulation was opaque. Galileo did not do a mathematical formulation of the calculus. He only looked at specific changes, but he did not go as far as Newton did and create a general set of rules and created the mathematics around the calculus so that other derivations could be done. Well, what ended up happening is that Kepler's laws, as a result of Newton's development of the calculus, were derivable from his three laws and from his law of gravitation. You can derive Kepler's p² = a³ law straight from Newton's laws. it just falls out. The shape of an ellipse also falls out if Newton's laws are used, which is really quite amazing. So you can take Newton's 3 laws of motion, the calculus, and he derived to actually manipulate it, and what I would call the axiom, or starting point, or law of gravitation, where we just said the force due to gravity is this thing. So it was a definition. It's an interesting thing. It's a starting point. And you can actually derive Kepler's laws and show that all of these things occur. Well, the next thing we say is, well, we can derive the orbital masses and say, well, remember we had this thing where the sun was at the center of an ellipse, one of the foci of the ellipse, and the Earth went around the focus and the sun was stable and steady? That's not entirely true. What the two masses do is they orbit their center of mass. So Newton's law says because that they're always equal and opposite, that as the Earth goes around the sun in a very, very, very little sense also goes around the Earth. But so what does that mean? All right. So Newton's laws can say, take a couple of kids and put them on a teeter-totter, like a little balancing teeter-totter thing. And if one kid's bigger than another kid, then what do you got to do? The big kid's got to sit really close to the fulcrum of the teeter-totter, and the little kid's got to sit very far on the end of the teeter-totter. And as they, well, let's see, if the teeter center is here, and here's a big kid, and your little kid's here, so then as they go, the little kid moves up and down a lot to balance the big kid. So we can think of it in terms of lever arms. The center of mass between the big kid and the little kid is close to the big kid on the teeter-totter. So we got this teeter-totter thing. Now in space, there's no teeter-totter. You can go all the way around. So the sun's much more massive than the Earth. Therefore, since the sun's so much more massive, the center of mass is closer to the center of the sun. That's all it is. Same thing with the Earth and the Moon system. The Earth and the Moon, they orbit a common center of mass. That center of mass is inside of the Earth, just in the same way the center of mass is inside the center of the sun. So the sun's wobble as it goes around the center of mass with respect to the Earth is very small. The Earth's wobble going around with the Moon is much larger because the Moon's mass is large, and it's close to the Earth. So their center of mass is getting closer to the Moon. If you talk about something like the planet Pluto, Pluto and Charon orbit a common center of mass, and their center of mass is between them. So they go around like this. They go around each other. In fact, we know about binary stars, which we talked about very long ago. Two stars that are seen to be orbiting each other in the sky, and they orbit a common center of mass. So binary stars are seen to orbit common centers of mass, which is the balance point between the mass of them as they move. And the common center of mass arises out of the necessity of equal and opposite motions, as well as, specifically the equal and opposite motions. It creates a center of mass. And the center of mass then is the thing that might move as a group through it. So we talk about everything in terms of their center of mass. So the sun and the Earth orbit a common center of mass. The sun and Jupiter do. In fact, if we take all the planets and put them together, we can say the entire solar system as a thing orbits a center of mass. And that center of mass is in one place. And the sun orbits that center. So it's kind of wobbling around a little bit, because all the planets are very small. But Jupiter's pretty big. It's bigger than all the other planets combined. So as we look at Jupiter and all the planets, we see that the wobble of the sun is pretty big due to Jupiter. And when we look at variable stars later, we will find that this wobble due to planets can actually be measured and it can actually tell us the masses of planets around distant stars. And so we can learn a lot using that. And this all comes from Newton's laws of gravity, which were published in 1687, which is an astonishing thing. So Newton's laws tell us about the nature of this thing. But here's the thing. Remember that old parallax thing that came up? Now, Newton's laws are really important. They give us a framework, a mathematical framework, an easily used mathematical framework for discussing the center of the universe, discussing how things move. But yet, no one, not even Newton, none of Newton's contemporaries had yet measured the Coriolis effect, nor had anybody measured the parallax effect. So is this all just smoke and mirrors? Is this real? Is the movement of the Earth real, or is it just a mathematical construct? And we'll look at that next time. See you soon.